Welcome to Module 4. We're going to be talking about chemical process applications of the first and second laws in this module. So our goal here is that by the end of this you will be able to apply material balances, energy balances, and entropy balances to solve engineering problems for real processes. So we've looked at these balances before. Chemical engineers largely focus on the steady-state systems. There are also many, particularly bio-related systems that are going to be batch, but we're going to mostly focus on the steady-state systems. Now that means the mass balance just simply means mass in equals mass out. Whatever streams there are, whatever comes in has to come out because it's not allowed to accumulate in a steady-state system. The first law says that the heat transfer equals the work plus the change from inlet to outlet of the total energy, where the energy is a combination of the enthalpy, the kinetic energy, and the potential energy. And then our second law says that the change in entropy, inlet to outlet, is the sum of the heat transfers divided by the temperature that occurs at, plus any entropy generated. There's a lot of equipment that can be modeled as a steady-state process. Now, in the course learning management system, we have a copy of this handout so that you can print it and make it more legible if that will help you. But basically, the types of systems that we usually look at are going to involve things like compressors, nozzles, throttling valves, heat exchangers, pumps, turbines, and mixers. Those are the most common units. So let's look at these and what the standard assumptions should be. So a compressor, I've drawn a sketch of one style of drawing a compressor. Its job is to take a gas and increase the pressure of that gas, usually to cause it to move through a system. Sometimes the purpose is merely to just increase the pressure, not really to induce movement. Now normally these things are going to be insulated, in which case Q will be 0. They require work, so using the convention that work required is negative and work developed is positive, this is going to be negative work. And the enthalpy change is typically going to be positive. Frequently we can assume that the kinetic energy is going to be 0, simply because most of the time I'm just doing this to increase the pressure or to just keep it moving. But in a blower, which is a form of compressor, the kinetic energy term will need to be included. Potential energy change is virtually always 0. We usually are not using this to drive a large altitude change because that's insignificant with gases. Nozzles and diffusers are systems where I can either narrow the area or open up the area for the flow. Typically, I'm going to have Q as more or less 0, simply because these are typically very small devices, and so there's not even much chance for them to lose heat. The work is going to be 0 because there are no moving parts. Kinetic energy, usually the entire purpose of putting this in there is that kinetic energy is intended to change, either to slow down a process in a diffuser or to speed up the fluid in a nozzle. But the potential energy change will be 0. And if everything else is 0 except for the kinetic energy change, then the enthalpy change must also be non-zero to compensate for that change in kinetic energy. A throttling valve is another really important piece of equipment for us, and it's so simple. It's kind of like a nozzle and a diffuser back-to-back. I frequently call it a torture device for fluids. So what we're going to do is we're going to take this fluid and we're going to squish it and then expand it back so that the net effect is no change in kinetic energy. And they're small, so no change in potential energy. They're small, so not much space to lose heat. And there's no moving parts, so no work. And so because of the first law, the energy balance, I end up that the enthalpy doesn't change. So that's an unusual result. It's not an assumption I'm making. It is simply because everything else was zero. The only way for that to work in an energy balance is for the delta H to be zero. Now, heat exchangers can be analyzed either as a single fluid or with two fluids at the same time. So if I study just one fluid at a time, then heat is going into or out of that fluid. So Q is never zero if I do this form of analysis. The work, however, will be zero because, again, it requires moving parts, and this is just a fluid flowing through a device. There's going to be an energy change. Part of that heat transfer is going to change the energy, so delta H will not be zero, but usually there is little to no kinetic or potential energy change. I am frequently going to assume that the pressure is constant. I also am going to assume that if it's a heat exchanger, it's exchanging with another fluid. So one of those is going to gain heat and the other one is going to lose heat to that first fluid. So therefore, the amount of heat transfer for the two fluids will be equal to each other, but in opposite directions. Which leads me to analyzing a heat exchanger for both fluids at the same time. In that case, I'm going to insulate this thing like crazy because I want all of that heat that's being exchanged to go to the other fluid. No moving parts, so work is zero. There's no reason to assume that kinetic energy is going to be zero because I'm expecting that to change. That's kind of the purpose here. But I am going to have multiple streams in and out. Kinetic energy, potential energy still will be zero. I am going to have to analyze this as if there's more than one stream in and out. But for each one of those streams, pressure is constant. Next very, very important category of equipment is the pump. A pump is very similar to a compressor except for it works for liquids. And because of that, it's going to end up changing some of the things we have to do in the analysis. But the basic assumptions are typically true. Now, a pump is frequently insulated, in which case Q is zero. Sometimes the pump, by increasing the pressure on the liquid, it's going to heat the workings of the pump, the bearings primarily, so much that they are going to mechanically fail. And so what we would do in that case is we will add cooling to our pump. So I may have Q less than zero if I have a cooled pump. Now there is going to be work required, depending on your sign convention. If I'm assuming that work required is negative, then this is going to be negative work. Delta H is going to typically be positive. It will have more energy as it leaves the system. The kinetic and potential energy changes may be zero, they may not be. You need to always be very careful in your analysis and decide where the inlet and the exit states are. This is going to be exclusively used for liquids, and the pressure will increase across the pump. A turbine is an important piece of equipment in power plants. A turbine is going to take in a gas at a high energy state and have it rotate some equipment, and that's going to produce some power and deplete the energy of that gas. So as it passes through the turbine, the pressure of this gas is going to decrease. Now, frequently we are going to insulate these things so that all of that energy is going into producing power, not into the environment. You may also choose to cool these. Okay. There are various kinds of things you can do, but usually Q is zero. It may be negative. It's possible it could be positive. Work, however, for a turbine is always going to be produced. That's the purpose of a turbine. It will produce power. So therefore, work with a standard sign convention is going to be positive. Delta H will be negative because I'm going to be depleting the energy of the fluid to produce this power. Kinetic energy is typically zero, but not always. changes in potential energy are virtually always negligible because it is a gas. No matter what the change in elevation, because it's a gas, it's probably not going to be worth dealing with. The last type that we've got in this summary sheet here is the mixer. Now, a mixer is going to bring in multiple fluids. They may have different energies, and they're going to all be combined into a single stream. We usually assume that this is going to be insulated, so Q is 0. There are no moving parts, so if no moving parts, it's basically like a T in a pipe, so there's no work required there. There's not going to be any significant kinetic or potential energy changes generally, and so I'm going to end up in the first law. When I put my energy balance together, I end up with the net is going to have no enthalpy change. But remember, each of these have different flow rates, multiple streams coming in and a single stream coming out. And so that's the net delta H is 0. But if I follow any particular molecule, it's going to have an energy change. Now, there's only one way I can get this mixer to work. I have to make sure that all streams are at the same pressure. If I have any stream at a different pressure, the mixer will fail. Okay? All of the fluid will go from the high pressure to the low pressure. So this is going to conclude our first video in Lesson 4. When we come back, we'll look at some examples.